And we are now live. Cool. All right. Hey.
I got a haircut today just for you guys.
Really? I'm.
That's really kind of you.
So did I.
I look like a hobo.
I start my project beard whenever I start like a big long-term project. I start growing my beard just as a reminder that the project is ongoing and we're not done yet. So I'm getting more and more like a mountain man every day. So we should be another. I hope we completely redesigned the universe today. Moved to an entirely new server. It's so much faster. It's so much better. Almost just I just have to shut down the old server and then we're done. So
have we figured out if starting these things through the YouTube live thing is different than setting it up through Google+? Does that work better?
We haven't done the experimenting yet.
That seems like a big platform there that Google's putting a lot of energy behind.
Yeah, and in fact, they're doing a lot of it through the gaming platform. So they're trying to be kind of like Twitch, and so we could run, we could parasite in on that whole gaming platform. So you've put it in my brain, and we'll do that. We'll try and figure that out for next week. We'll try coming at it from a completely different direction and set up via the gaming platform, and then maybe we'll play some video games too. So I'm going to say hi to some people while we're hanging out here, if they're there. I hope they're there. Yeah! Stephen Alvey, and Matt Woods, and Ben Kalo, and Jim Meeker, and Billy Gordon, and Nancy Graziano, and Rick Schwartz, and Ray Vince, Guido Bibra, Ryan Schmitz, Michael Jobin, Susan Hunter, Linda Sadek, Eric Briggs, Graham Ash. I already said Tony Lynch, didn't I? Okay, Thomas Traniker, Giselle Severin, David Dunn, and I'm going to say hi to Nancy Graziano for a second time because she's so awesome. And so if you're wondering why I'm saying how I know to say hello to these people, how do you get a chance for me to say hello to you, all you got to do is use the Q&A app, so wherever you're watching this, just click on the video and it will bring you into the Q&A app, and you'll still be able to watch the video, but then there'll be a bunch of questions that you can ask us and the guest. It's 12:05, so I'm gonna switch from rambling mode. Oh, it says no viewers yet. I don't know. All right, I'm gonna start it up. If anyone says that they can see this, if someone says they can see it, then I will start it up. Come on, somebody. Can you see this?
I assume we don't count.
No, no.
So it is amazing that we can do this, Steve, when it actually works.
Yeah.
Yeah.
The sheen wears off quickly when it doesn't work.
We might need you to go over and give the whack to the Google computer.
That's right. I can almost hit him from here with a rock.
Yeah, still no. I don't think people can see us.
Can somebody type into the event page and ask there?
Yeah, I see the live site.
Yeah, no one's saying anything.
Yeah.
No one is saying anything.
Wah, wah. Let me try watching it on the...
Yeah, my girlfriend says that she cannot see it as a live event.
Oh no.
I can see it on... Yeah, I can see it when I watch it from outside.
Interesting.
Not one person is saying... Oh, it says 4 viewers, so I think it has kicked in now.
Okay.
So just in case no one heard me say that, can you see... Now the viewers are coming in now. Okay, great.
All right.
Well, I'm going to do this again just because it's totally unfair to not say hi to everybody. So I'm going to say hi to Stephen Albee, Matt Woods, Jim Meeker, Billy Gordon, Nancy Graziano, Guido Bibra, Rick Schwartz, Ben Kalo, Benjamin Valmont, Michael Jobin, Ray Vince, David Dunn, Ryan Schmitz, Thomas Traniker, Michael Jobin, Tony Lynch, Graham Ash, Susan Hunter, Eric Briggs, Linda Sadek, Giselle Sabarin, and a second time, Nancy Graziano. But that's actually a fourth. But because you probably missed the hellos before.
We did.
Let it begin. Hey everyone, my name is Fraser Cain. I'm the publisher of the Universe Today, and this is your weekly space hangout for Friday, January 15th, 2016. We've got a very cool show for you today. So we've got our regular rundown of astronomy stories. We're going to be talking about This Week in Musk. We're going to be talking about a star that's been dimming for a century, other space partners joining for ISS resupply, astronomy harassment, China's plans to land on the far side of the moon, death throes of a giant star, and a black hole shutting off. And we've got a special guest, but we'll get to that in 1 second. So joining us this week, we've got Kimberly Cartier. Hey, Kimberly.
Hi, Fraser. Hello, viewers.
We can hear you. Okay, great. We got
Fantastic.
Morgan Renberg. Hey, Morgan.
Hey, Fraser.
We got Paul Sutter. Hey, Paul.
How's it going?
Good. Are you in stateside or are you in Italy?
I'm in the U.S. right now. This is
All
my
right.
American plant.
That's your American plan.
Yes,
I never remember which one is which. Awesome. Great, okay, and joining us this week, we've got a special guest, Dr. Steve Howell from NASA, who works with Kepler. Hey, Steve, welcome to the show.
Hey, Fraser, how are you? Thanks a lot. It's great to be here.
All right, so as always, we're going to take a few minutes to talk to Steve, ask all of our questions of all of our gyro-related questions about Kepler.
Yes.
And then we'll get on to the rest of the news story. So feel free to ask some questions. Again, just use the Q&A app, and I'll keep an eye on them and sort of keep track of time. And hopefully, we'll be able to get through a bunch of your questions about aliens, about gyros, why spacecraft don't have enough gyros, what we can do about that. All right, so let's go. So Steve, for people who maybe don't know who you are and what you do, can you give a quick intro for us?
Sure, let me tell you, the gyros reminded me it's lunchtime here, so we could have those heroes there, gyro sandwiches. Anyway, yeah. So I work for NASA, as you said. I work out here in the San Francisco Bay Area, very near Google, as we talked about earlier in our beginning here. I'm called the project scientist for the Kepler mission and the new NASA K2 mission, which is a follow-on mission. So I have the greatest job in the world. I get to lead a whole bunch of scientists and engineers and think big thoughts about what cool science we should do with our space missions. Get to be involved in many kinds of science that all of our people that use our data do, and get to do fun things like this. So it's been quite a ride with both Kepler and now with K2 for about a year and a half.
And we've reported plenty on Kepler and many of the planets and the techniques and methods, and we've talked about sort of the original Kepler mission and then of course the K2 mission. How is Kepler doing right now?
Yeah, so right now we're doing really well. We have been doing the K2 version of the mission for about a year and a half. Just to let people know a little bit that's different about the two. So Kepler looked at one place in space for 4 years. For those of you that know, it was near the constellation of Lyra and Cygnus in the northern hemisphere. The K2 mission has to look in the ecliptic plane, which is known probably more widely as the zodiac. So we stare at all your favorite zodiac constellations throughout the year and do different kinds of science. We're still searching for exoplanets and finding really great exoplanets, which we can talk about in detail. I think those are of great interest. But we also are doing other types of science that Kepler couldn't do because its mission and where it looked. We're doing great things with star clusters, with cosmology, supernovae, various kinds of pulsating stars, planetary nebulae, just all sorts of things. So it's become a really broad mission, much more like Hubble than like the original Kepler.
But the target in terms of planet hunting, the target has changed for you, right? You're not looking at the same kinds of stars that you were with the original mission.
That's right, Fraser. The original mission looked at stars that were roughly the age of our sun, and that was done on purpose because the original mission wanted to find how many planets might be like our planet Earth orbiting a star that might be like our sun. We now are looking at stars that are much, much younger than our sun, and some stars that are much, much older than our sun. And in some of the very young stars, we're actually seeing stars that still have large disks of dust and gas around them where planets are just beginning to form. And so it's quite a variety of stars now of different places in the galaxy, stars that are very close to the Earth, stars that are very far away, sort of a whole big variety compared to Kepler.
And so now, I mean, you've been a couple of years into the mission. What are some of the really interesting discoveries that you've made so far?
Sure. Let me highlight a couple of them. I guess there's we've found so far about 350 new planet candidates with the K2 mission. Pretty soon, about 120 of those are going to be put in the category that we astronomers call validated. That means that in general, most of us believe they're probably real planets. And a couple really interesting cases there are one planet that was found, one planetary system that was found by K2 early on, is a system of 3 planets. They're very much like the Earth, slightly larger in size, but probably rocky in composition. They orbit in very close-in orbits to a low-mass star. The outer one of those is probably in what's called the habitable zone. That is a place where liquid water might exist on its surface. And this particular system is so bright, the host star is so bright, and the system is so close to the Earth, that it's probably one of the first rocky planet systems where we'll be able to measure the atmospheric composition of one of those planets. And that'll be very exciting because maybe we'll find signs of life in the atmosphere. Things like chlorophyll or free oxygen or perhaps pollution, very signatures of civilization or life.
Now, one of the tragedies with the original mission was the spacecraft failed just as you were starting to get to the place where you could start to find that holy grail, right? That Earth-sized world orbiting a sun-age size star within the habitable zone where liquid water could be present. Do you think there's any way to kind of get at some of those worlds out of the old data? You know, with the new one, you're not able to go after those same stars, right? So.
Yeah, so it's a little tricky. So the idea with the original mission was it was planned to be 4 years long. And the reason you go for 4 years is we had kind of a rule with the first mission that we would not believe a transit, we would not believe we found a planet unless we saw it orbit its star 3 times. So if you're looking for planets like the Earth, if you look for 4 years, you're likely to see it do an orbit 3 times. If you look shorter than that, you don't get enough. And so it just ended at almost exactly 4 years after launch, and we're going through the final look-see of that 4-year data set. And I think that in the end, which will be sometime this summer, we'll have a number of really good candidates for relatively small planets orbiting stars like the Sun that are relatively small, perhaps not quite as small as the Earth, but small enough that we know they're going to be rocky. So I think we'll be able to tease that out of the data. Something
we could call Earth 2.0?
That's right, something that I think will be more like an Earth 2.0 than anything we've found so far. K2, you're right, it only looks at each individual field for about 80 days, so it's difficult, of course, to find a planet that would have a 1-year orbital period. But one of the great legacies of the original Kepler mission, which we're putting to good use in the new K2 mission, is we know now the way our telescope works, we know how well our data is calibrated, and so if we find even a single transit now, just one observation, we don't need the 3 observation rule anymore. We believe that that's probably good enough for us to then do extensive follow-up work and prove that that object's a planet. So now with one measurement, we're going after them.
So in other words, just by seeing the amount of light that it blocks and sort of the time that it takes to cross the star, you think that's enough for you to be able to really be able to know the size and perhaps even orbit?
It's enough for us to make a guess at the orbit. It's enough for us to make a really good guess at the size. And it's enough information that we and the world community will go and do observations with other telescopes to prove or disprove that that might be a planet like the Earth and might be in an orbital period like the Earth's.
Right, and so lining up a telescope to watch when you know that transit is going to happen is much easier than trying to just wait and stare at the.
That's right. Yeah.
Sky. So I was, that's just one great example of some of the innovations that you came with as part of this mission, both in terms of, the ideas on how to search for planets, but also sort of the clever ideas to rescue the mission, which had failed. I would love to know kind of more of these kinds of solutions that you were able to come up with, because that's just fascinating.
Yeah, it was one of those great things. It was sort of a 9-month period where we were on pins and needles between the gyroscopes, the reaction wheels failing on Kepler, and figuring out how to run this new K2 mission. And of course, many kudos go out to the engineers at Ball Aerospace that did a lot of work on that and putting together how we could possibly operate it. And then at this end, the scientists, we talked and thought about what science program we might be able to do. So to give you an example, we actually now balance the spacecraft. So we had used the 2 remaining wheels that are working fine and look like they're going to last for at least another 10 years probably, even though we have 2 more years of fuel left. those are balanced now against the pressure that's on the spacecraft by the light of the sun. So not the solar wind, but the actual light from the sun that pushes on the solar panels of the spacecraft. And it pushes with the force of 2 mosquitoes landing on a pool table. So that's the amount of force that we need to balance. And it doesn't seem like much, but of course when you're out in space in a zero gravity environment, that's a big deal.
That's just absolutely amazing to me. I mean, the running joke in this show is that there aren't enough reaction wheels put on any spacecraft, and somebody actually mocked up a spacecraft where the thing was made almost entirely of reaction wheels.
Yeah,
and that may be enough. So, that problem does keep coming up, and I've never had a chance to ask someone sort of this close to the problem. Is there, has anyone said, like take however many reaction wheels you need and double it? Is there any reason, will that be the future?
It probably won't be the future, and the reason is mostly a matter of cost and weight. When you launch something from the Earth, so weight is the big factor, and so the more things you pile onto it, the more it costs to literally launch it off the surface of the Earth. And in addition, if you buy more and more reaction wheels, it means you buy less and less science. So if you launched a spacecraft that had lots of reaction wheels but no scientific instruments, it probably would run forever, but who would care? I mean, it's
I can look at any science poorly.
That's right, yeah. So there's this balance in there somewhere between how many you can afford and how much weight you can do. Kepler, like most things, was launched with a spare. We had 4 reaction wheels at the beginning. And so when the first one failed, we just thought, great, good thing we put a spare on there. And of course, you could now say, well, we only have 2 good ones. Maybe we should have launched with 6. You can always say that. And most things get launched with a few extra reaction wheels, but they can't have an infinite number.
Infinite number of reaction wheels, yeah.
Yeah.
So we are, with the discoveries, the size of them coming down, they're finding these planets in the habitable zone. We are on the edge of, what could be answering the most important question that human beings can even ask themselves, the most important scientific question, which is, are we alone in the universe? Where are we now, do you think, for being able to have an observatory that could go up, that could get to that answer?
Yeah, that's a good question. Well, I'll just start with my personal answer. And again, my personal answer is, of course, we're not alone. I mean, if you think about from the statistics of Kepler, how many planets that could exist even in our own galaxy that would be, similar in size and similar in conditions to our own Earth, it's a staggering number. It's 20 million or something like that. So I think the chances of us being alone are 0. But I think your question more about is proving that. Can we find another planet and point to it in the sky and say that one right there?
Yeah, and Enrico Fermi has some pretty difficult questions for you to answer.
He does, indeed, he does. And if only he were here today, Fraser, we could talk to him. But yeah, so I think, in my mind, I think one of the proofs to me would be that we would actually be able to measure some atmospheric component that we would know must be a signature of life. And now we wouldn't know if it's bacteria or elephants crawling around on the surface or whatever, but we would know there was life. And I think that's the first great thing. And I believe we'll see that in the next 10 years with one of the planets, probably from K2, because they're going to be bright stars and very close to us. And then, of course, NASA is looking into, as well as the European Space Agency and many other people in the world, are looking into launching something that's going to image some planet orbiting some other star. And that image, while it won't look pretty like the Earth looks from a spacecraft orbiting the Earth, but it'll be able to see if that planet has kind of the right color and maybe the right surface compositions, and that it is indeed rocky on the surface. So that's probably going to be a little longer out, maybe 20 or 30 years.
But it's kind of amazing, right? Just a couple of generations that we will either have, we'll be, yes, we're not alone, there's life there on that planet, and in fact, they probably just invented the steam engine, right?
Absolutely. Yep.
Or this is super weird, we're not seeing any life in a larger and larger bubble of space, and it's starting to freak us out.
I agree. I think either of those answers is great. The second one's scary. More than the first one there. Yeah, I mean, Fermi had a point, and I think that one of the things Fermi and other people that think about that don't consider is things are far apart in space. I mean, we are really, really far apart. Even our nearest stars are not that close. And I grew up, and maybe many people listening grew up with the original Star Trek and now the new Star Treks. And boy, it'd be great if we had warp drive, so we could zip around the things, but we don't. And the reality is we may never have something like that. So communications, perhaps the best we'll ever do is going to be radio signals, and even that is going to be a very slow process in communicating with someone else.
Now, what about getting at those planets that aren't transiting directly in front of the star? I mean, we know there's, most of the methods, the radial velocity method, the transit method, the gravitational microlensing, they're all using that same technique, that you really need things to be aligned perfectly. Are there any methods in the works to maybe find some planets that aren't directly lined up yet?
Sure. Well, the transit method certainly relies on that, but the other methods you mentioned don't necessarily need them lined up. It works a little better that way. You get more information that way, but you can find a planet via radial velocities in any orbit around the star, essentially. The real power is if you find both a planet with radial velocities and a planet that's transiting, then the power of that particular system is sort of multiplied, because now you know that it cuts right in front of the star, and you can make measurements of the planet as it passes in front of its star. And the radial velocities allow you to know its mass, and if you put its mass together with the radius that you measure from a transit, those two with some simple math give you the average density of the planet. And if you get an average density that's like a rock on the Earth, that's a pretty exciting result compared to the average density of helium or something like a Jupiter.
So I've got a few questions from the viewers, and I thought we would get cracking into some of those. So this comes from Bjorn Larson. Is K2 discovering asteroids and Kuiper Belt objects as well? So do you have any capability to see those kinds of objects?
Sure, that's a great question. Yeah, K2, as I mentioned earlier, is in the ecliptic plane, so in every place we point, we see lots and lots of objects in our own solar system. And so we're finding new asteroids that the asteroid people are working on, but we're also making detailed observations of known objects. We recently made an observation of an object in the Kuiper Belt, and using our observations and some other data showed that it's now the third largest Kuiper Belt object, so only 2 behind Pluto. So yeah, we're doing lots of solar system science with K2.
And what about finding those kinds of objects in other solar systems?
That's tough. I mean, Kuiper Belt objects, while we know and love them, and Pluto is still my favorite planet, the Kuiper Belt objects are very, very tiny little pieces of rock, and so seeing those in other solar systems will be tricky, although there have been a few examples that we found. For example, K2 recently found a disintegrating planet or a swarm of Kuiper Belt objects or comets orbiting a white dwarf star, a remnant of a past star like our sun that has exploded and left this white dwarf as a core.
So I got a question from Adam Synergy. Let's see, so he's broken up into 3 parts here, so we'll see, get through here. So planetary candidates are assumed to orbit a single star, but an unknown, non-negligible fraction must statistically be orbiting in multiple star systems. So will these produce false signals? So, what kind of work has been done to find planets in multiple star systems?
Wow, that's a fabulous question and a second level of detail, so good for that viewer. Yeah, so there's been certainly some work done by myself, in fact, on high-resolution imaging and my group who works on that, and some other people that have shown that stars that have planets orbiting them probably come as binary stars about half of the time. This shouldn't really shock anybody who knows about astronomy, because we've learned since day one that about half the stars are in binary systems. So we've now shown that that's true also for stars that host planets. So we now have sort of 3 kinds of planets, if you want to talk about that. We have planets that orbit single stars, like our solar system. We have planets that orbit around one of the stars of a binary system, and in fact, often it's very difficult for us to know which star they orbit. We know they're there, but we don't necessarily know which star they orbit. And then the third class of this, which was discovered by the Kepler mission, and we'll see more of this with K2, are planets that orbit around a double star. So you have 2 stars orbiting around each other, but far out from those 2 is a planet that actually orbits both of those stars. So as we might imagine, it's a much more complicated system than we thought. We're finding all kinds of those, and the devil's in the details, of course, of figuring all that out.
And I guess the surprise is that these actually could be stable and not eject the planets out.
That's right.
As long
That's
as
right.
the
That was a
distances are
surprise.
far enough. Yeah.
Yeah, as long as the distances are far enough or the two stars are far enough apart, then everything's okay.
That's amazing. So this comes from SciJoy. Are there any citizen science projects that accompany K2? How can we get students involved?
Oh, my goodness, that's a good question. Yeah, so there's an enormously large amount of citizen science going on that started with Kepler and continues into K2. The most famous one is probably Planet Hunters, which started out as a group that had a mission to find planets that the Kepler project didn't find, and that has evolved into an enormous outpouring of community around the world that now look at light curves from both Kepler and K2 and other missions and discover not only additional planets, but discover all sorts of interesting astrophysical objects. That's the most interesting one, and the largest one probably. But there are many, many more. I mean, there's a number of us, including myself, that have projects with students from junior high school all the way up through college that take our data from Kepler or K2 and combine it with data from other space telescopes or ground-based telescopes. All the data is public. All the data is available to anybody who wishes to use it. So it's just a non-stop community fun.
So if you're a teacher and you want to get your students involved in some of these projects, where should they look?
Yeah, they can look at a couple resources. There's one is our website. You can look up the K2 or Kepler Science Center. We have a lot of educational materials there to get you started. You can contact the NASA Education Institute at the Jet Propulsion Laboratory for exoplanet research. They have a lot of material there that can help you. Or you can send me an email, and I'm happy to point you in the right direction or tell you what things we can get involved in either as a group or by yourself.
And there's a lot of amateurs, you know, if you have a telescope, a lot of amateur astronomers are getting involved in more on the gravitational microlensing side, but helping actually discover planets.
Yeah, absolutely. It's a great game. As I mentioned before, the stars, in particular that K2 is looking at, are very bright. Many of them are stars you can see with your naked eye. And so any help we can get, in particular from people with relatively small telescopes, is fabulous because most professional observatories can't look at stars that bright. It's kind of a weird thing, but the stars are too bright for their large telescopes.
Yeah, it's amazing. All right, so let's see. So Matt Woods wants to know, what is the process that you use to confirm that a potential planet is actually a planet?
Yeah, that's a great question. So it's a long and grueling process. Scientists, by their nature, are quite skeptical, and so if we find something that looks like a transit, it's kind of like looks like a duck, but of course you want to prove it's a duck, and so you have to go through a lot of processes to do that. It's a little easier, I would say, now than it was when Kepler first started, because now everybody's kind of drank the Kool-Aid, and we all believe that most of the signals we see are in fact planets and real planets. But it's still a process. It requires eliminating other causes to that. And that requires a lot of extra telescope use with telescopes on the ground, sometimes large, sometimes small, usually a combination of that, which take measurements like high-resolution imaging to look for stars that could be the source of the transit-like event, spectroscopy that makes us learn about the star that we think the planet orbits. Sometimes telescopes in space, different wavelength observations are quite common. We observe in the optical bands, but sometimes observing the infrared helps. So it's quite a process, and then usually people write a scientific paper that gets reviewed by some other scientists, and if you can convince them and that paper then gets approved, then we all believe it's a planet.
All right. So I think why don't we'll move to the news portion, but you're going to stick around and we've got some planet talk. So why don't you join us for the rest of the show, and
Sure.
Maybe we'll throw a few zingers your way as we move through, and maybe if people have some other questions they want to ask Steve over the course of this show, just go ahead and just type them into the Q&A app, and we'll sort of percolate them through till the end. So let's move on to the actually, and for anyone who maybe needs to roll, how can people find out more about you and what you do if they want to find out more information?
Sure. If you want to find out, the easiest way is just go to any browser you want to use and type in the K2 or the Kepler Science Center. That will take you to an enormous number of pages with links to all sorts of things. Perfect. And you can find out everything about the missions and myself there if you want.
That's fantastic. Okay, great. All right, Kimberly, we're going to start with you this week. Let's talk about KIC 8462, which everyone is super excited about.
Yeah, so if the name KIC 8462 sounds familiar to you, it's because that's the same star that had made headlines not too long ago by having a potential alien megastructure around it, and my name is attached to that, and all of that fun stuff that happened. So while it may have sort of faded from public eye, astronomers are still very excited about this particular star and have been doing a lot of follow-up work. So as a reminder, this is the star that had very strange, very anomalous Kepler transit signals that were very irregular in shape and depth and periodicity that led to a lot of speculation as to what could be the physical cause of such strangeness. But a recent study has found that this star has been strange for more than just the lifetime of the Kepler mission. An astronomer at Louisiana State University actually went back into the Harvard archives, looked at thousands of old photographic plates from old telescopes, looking at the behavior of KIC 8462 over the past 100 years, and have found that this star has actually been getting dimmer and dimmer at a non-constant rate over the past 100 years. It's dimmed for over 100 years he looked at it, and it's dimmed 0.2 of a magnitude. And this type of star just doesn't do that. There are no other stars in the sky we've studied that show this kind of systematic dimming over a 100-year period. And so we're sort of scratching our heads again, wondering what the heck is going on with this star.
Because that kind of does sound like an alien megastructure under construction, doesn't it? And as they're moving through, moving towards a fully operational alien megastructure.
Yeah, we're still trying to find a compelling physical reason that such a star would be dimming that much over a 100-year period. There are some potential physical things, like a giant cometary cloud slowly moving in front of the star, causing it and no other stars in the vicinity to dim. Maybe. We're still trying to figure it out, but it throws up a flag that this star is behaving so strangely over such a long period of time. We can't tell with the time resolution of these photographic plates. We can't tell whether there are additional strange transit signals during this time, just because the plates are spaced too far apart for us to determine that. But it means that a lot of people are going to keep studying this star for a long time, trying to figure out what the heck is going on.
So does this mean that you have to explain these two things now? The strange dimming for a type of star that doesn't normally dim, and also the weird transiting that was going on?
We do have to explain both of them, and being scientists and being skeptical, like you said, we would prefer that there be one compelling, naturally occurring reason why both of these things would be happening to the same star, because it's much less likely that there are two strange phenomena happening at the same time to the same object. So hopefully we can come up with one cohesive physical reason why the star has both been dimming over a long period of time and shows strange transit signals.
All right, I got to ask Steve then. So, do you have sort of a place in your heart where you're hoping that it's aliens?
I always have a place in my heart hoping for aliens. I wish they would land in my backyard any day, but so far that hasn't happened. This star is a very interesting star. It, of course, as you know and alluded to, became very famous a while ago. It's one of probably 5 objects that have similar looking, not identical, but similar looking weird dips and weird transit-like features in their light curves as measured by both Kepler and some new ones found by K2 as well. So I don't think it's alone in the only contestant as being an alien megastructure, although I think in all cases, unfortunately, I would say that's probably not the right explanation for what it is. It's probably things like swarms of comets or breaking up planets or many things we don't understand, but the fact that it's not alone, I think, means that either there are a lot of aliens out there, which there could be, but I don't think this is our signature, or we're seeing some interesting phenomena that we don't know about.
Yeah, I mean, we have this, this bias of only knowing, of really having one sample. We only have the solar system. We only see the kinds of things that are in this solar system. So it could be that there is some other, as you say, some other phenomenon, be it the giant cloud, the giant asteroid cloud that all solar systems have, that we just don't happen to have one of them.
Yeah,
But,
absolutely. Yeah, we certainly know from Kepler, who looked at an enormous sample of other solar systems, that so far there's almost anything you want you can find. Any kind of strange system you want to look for, it's probably been discovered or will be discovered. And so the universe is a strange place, and that's really cool for scientists. And this object is clearly one of the strange places we need to investigate further.
Yeah, this is the shape of astronomy to come, starting with things like Kepler, but as we move to the enormous data sets that we're going to generate with telescopes like LSST, we're going to enter this period where we suddenly discover so many things that don't fit within our previous understanding of the way the universe works. And for a long time here, sort of our understanding of the universe has moved up sort of in parallel with our ability to interrogate it. But now we're suddenly going to see hundreds, thousands, millions of stars and planets and objects that don't conform at all to what we've expected in the past. And it's going to really sort of snow us under for a little bit before we start digging out what exactly all of this means.
So Kimberly, I mean, you worked on the original, the original research for this planet or star, or who knows what it is. Are you going to come back around and do more work on this object?
Well, I know for certain that there are astronomers in my department and other people we're collaborating with that are still very excited about this and are planning future observations this month, next month, hopefully many months to come to work on it. So maybe my name will be attached to some of that again. I'd love to look at this target more in the future to just try and figure out what is going on.
Yeah, that's great. It sounds like, I mean, if it is an entirely new phenomenon, it's bordering on something that you could base a whole stream of research on, these kinds of objects. So
maybe that'll be the title of my thesis one day. One day.
What you received your Nobel Prize for?
Oh, well, I have a shelf ready for it over there.
Do you? Okay, great. Yeah, it'll fit really nicely over there. That's perfect.
Yeah. Well, just to put a plug in for the alien megastructures thing, there's a science fiction story that's a fairly recent science fiction story in a book called A Kepler's Dozen that talks about exactly this kind of object being used as a alien communication device to send us coded messages. So
I wrote
Kimberly,
a paper about that.
Yeah.
You wrote a paper or you read a paper?
No, I wrote
did
a paper about decoding signals from these types of objects.
Wow.
Extracting information from them.
Can you link that to me after the show? And
yes.
When did you
I
write
can do that? That was part of the part of the original alien megastructures thing. It's a very long paper, and the beginning talks about why it could be an alien megastructure, and the second part, which is where my contributions come in, tells you how to decode information coming from these signals.
Oh, that's really cool. Okay.
So I will send a link to that.
That would be great. Thank you so much. Okay, well, let's move on. We could talk about alien megastructures all day, but why don't we talk to we'll talk to Morgan about let's talk about with Sierra Nevada.
Yeah. So for the last couple of years now, private space companies have been the workhorses for launching supplies to the International Space Station. And this has largely worked well in the face of launch accidents by Orbital Space Sciences as well as SpaceX. But NASA is clearly quite satisfied with the performance of these private companies because it's offered three companies, Orbital, SpaceX, and Sierra Nevada, 8-year contracts to deliver cargo to the International Space Station. And this will actually take NASA's supply plan all the way through the intended end of the ISS in 2024. And there's sort of two big interesting things about this story. The first is that they've added a new contributor to commercial space cargo, and that's the Sierra Nevada Corporation. And they actually lost out the competition for the first round of this to SpaceX and to Boeing, but now that they've improved upon their spacecraft, their design, and their plan, they've been handed a contract along the same lines of all the others. And that's despite the fact that Sierra Nevada's spacecraft is quite different than all of the other spacecraft currently delivering cargo to the International Space Station. Instead of this sort of Apollo-era capsule that we see being used by SpaceX, by Boeing, by the Russians, by Orbital, etc., the Sierra Nevada Dream Chaser is a space plane, and it looks very much like a shrunken-down space shuttle. It launches vertically atop in Atlas V, just like Boeing's capsule does, but instead of parachuting back down with a heat shield, it glides back onto a smooth landing, just like the space shuttle did. And Sierra Nevada says that this allows for the safe and smooth return of larger amounts of cargo, and they hope ultimately one day people as well. But the other big exciting part of this story is that because they've engaged so many companies now for delivering cargo to the space station, we have all 4 American private companies as well as the European Union and Russia. There's going to be frequent enough and large enough deliveries of cargo to the space station that NASA intends to increase the crew complement from 6 to 7. And that means that now for the next and last 8 years of the space station, we'll have another crew member on board at all times to carry out station maintenance, scientific experiments, etc. And this is really going to help increase the productivity of the space station over its final years.
And we're only a couple of days from that next barge landing attempt by SpaceX. So
that's right. SpaceX will be launching a weather satellite for NASA this coming week, and after depositing that satellite into orbit, the first stage of the Falcon 9 rocket will attempt to land on a barge floating now in the Pacific Ocean off the coast of California. This, of course, is in the wake of their successful landing on the land a couple of weeks ago. But as we've seen in the past, landing on a pitching and rolling barge is much more challenging than landing on the ground.
Yeah, but once again, if they can get that happening, then we get closer and closer to more and more reusable rockets, and then maybe we can launch a whole lot of reaction wheels into space with every mission.
There we go.
Yeah, we'll just make them reusable. Let's move on. Paul, let's talk about the death throes of a giant star and the puzzled researchers in its wake.
Yeah, I know. Aren't astronomers always puzzled and baffled and bamboozled? It seems like every other astronomy.
Astronomers, yeah.
So what's going on with Betelgeuse? It's a red giant star about to blow any day now, astronomically speaking. It's going to go supernova. But before one of these giant stars goes, they shed their outer layers of atmosphere in big waves. And we're not exactly sure what powers these waves of gas to come off, these big ejections. We thought it might have something to do with radiation pressure or magnetic fields, but some older radio observations and some more recent observations in the infrared show that the surface of Betelgeuse is actually rather cool. It's only like 500 K, which is like, I mean, it's not room temperature, but it's not far off. And there's just not the temperature you need to drive currents to get strong enough magnetic fields to push these winds through. You don't have the radiation intensity that you need to drive the gas. So we're not exactly sure what the physical mechanisms are to puff out these stars and get their gas ejected.
And these are some of the largest stars in the universe. I mean, these can be a pretty sizable object. So it's amazing that there's such an enormous size to them, and astronomers still are so bamboozled by what's going on here.
I like the bamboozled term.
I'm running with that. That's going to be the next article. Will be some physical property bamboozles, swindles astronomers.
Swindles were flummoxed. That's the problem. Because they're so big, the big stars are rare, or they're rarer than smaller stars, because one, it's hard to get big pockets of gas enough to make the big stars, and they don't live very long, so just statistically, if you take a snapshot of a galaxy, you're not going to see many. And since there's not as many stars, we don't have a lot of data on them, and with fewer data, it's harder to make hypotheses and draw conclusions and compare models against each other.
So does that have any impact then on the thoughts about things like Betelgeuse? Like they think it's going to detonate any day now. Is it possible that it's going to take longer? I guess can't say shorter, but it's going to take a little longer than we think, or?
Yeah, I mean, even the core collapse supernova mechanism isn't completely known. We don't fully understand what drives the supernova explosion itself. We do know that it's bound to happen, and that when stars are in this phase, we know that there's helium fusion in the core, there's silicon and oxygen fusion in the core, and that just can't last long because of the physics involved. So we know it's going to blow, but we just don't know exactly how.
And so really the holy grail in this field is to really recognize those signs before the thing is about to collapse, so that you can make your observations, and then the thing explodes, and you got a chance to see it before it died, and then
exactly. And then things like neutrino observatories are critical here, because they give us a peek inside of the star right before it goes supernova and during the supernova explosion, so we get a better picture than just looking at light. We get a better picture of what's going on in the interiors of these stars.
Fantastic. Okay, Morgan, let's talk about China landing on the far side of the moon.
So if you might remember back to 2013, when China landed the Chang'e 3 lander and its U-2 rover on the near side of the moon, and that rover drove around and collected some observations of the near side of the moon. That was China's first soft landing on another body in our solar system. Fast forward now about 2 years to the beginning of 2016, and China's announced that they're going to carry out a similar mission, but on the far side of the moon. On the far side, unlike what Pink Floyd would tell you, is not constantly in darkness, but just like the near side, it experiences very extreme shifts between being dark for 2 weeks on end and then being light for 2 weeks on end. And this is a challenging environment to survive in, and it's made even more challenging by the fact that the far side of the moon is that because it always remains facing away from the Earth. And this means that you can't just point your antenna back at Earth and communicate with mission control here at home. Instead, you need to have a spacecraft in orbit about the moon that's capable of collecting those signals and then relaying them back to Earth, and then relaying Earth commands back to the rover or the lander. And you can imagine that makes it a much more complicated task to undertake. So complicated, in fact, that no nation has ever attempted to land on the far side of the moon.
Yeah, I was just going to ask you that. So nobody has ever actually roved or landed on the far side of the moon. They've always been in direct visual radio contact with Earth.
So, right, that's right. We've made plenty of observations from orbit, originally with the Apollo orbiters, but then also later with the Lunar Reconnaissance Orbiter and other moon orbiting spacecraft. So we know very well from orbit what the surface of the moon is like on the far side, and we know that it's very different than the kind of surface that we see here on the near side of the moon. And so what China intends to do is to take the Chang'e 3 lander and upgrade it with more instruments and place it down on the far side of the moon, where it will be able to measure the surface and an atmosphere of the far side of the moon, and then we can compare that to the observations that Chang'e 3 made on the near side of the moon, and understand for the first time this sort of lunar dichotomy that we've had ever since we began observing the moon.
It's going to be absolutely amazing. I mean, the far side of the moon is so different. I mean, you look at the pictures of the surface of the moon, and the near side has these really familiar mare and the seas and the lava plains, but you look at the far side, and it's a lot more kind of crater pockmark, and they're still trying to come up with trying to understand the reasons why the far side is so different from the near side. To actually get robotic boots on the ground to pick it up and lick the rocks would be great.
Absolutely. It's going to really reveal a lot about the history of the far side of the moon, and that's going to help us understand the history of bodies in the early solar system, because unlike the Earth, the moon has remained relatively unchanged from 4 billion years ago when it formed. And that's information that we then apply all over the solar system to places that we can't go and touch to understand what's going on. And it's also a really big boon for China's space program, because they've been developing both their human and their robotic space programs in rapid succession, but they're also in competition with nations like India, who is currently orbiting Mars, and even the UAE, which is planning to launch a mission to Mars in 2020. And so as this sort of second space race heats up, doing something that no one, not the Russians, not the Americans, not the Europeans, not the Japanese have ever done, is going to be a real feather in the cap for China's space program going forward.
Yeah, we're also focused on SpaceX, but don't forget, right? The Chinese have landed on the moon, orbited the moon. They've put multiple humans in space. They've built a space station and had people on it, and they've got big plans. And I think they're going to pull these things off. They're going to do this. They're going to, I think they're going to be, we are seeing the second space race, and they are just accelerating their work. So, it's going to get pretty exciting.
It's extremely exciting.
Yeah.
Can't wait for the pictures.
You can't wait for the pictures. Yeah.
Can't wait for the
that would be amazing. I mean, just to see the far side of the moon up close is something that we've never seen. As it's only been orbital, so this will be groundbreaking if they pull it off. So go China! We can't wait. All right. So Paul, let's talk about a black hole shutting off and how it has been swindling astronomers.
No, we're not swindled. We understand this one.
Yeah.
A disappearing quasar that has pleasantly surprised astronomers. How about that? So quasars are supermassive black holes found in the centers of every galaxy, and when they're active, they're really bright. When gas is falling onto that black hole, the gas crunches down together, there's lots of friction, there's lots of heat, and it glows really brightly, and we can see it from across the universe. But when there's no gas, when it's either been ejected or if it's actually swallowed by the black hole, the quasar goes quiet and it just looks like a normal galaxy. And for the first time, with observations from the Sloan Digital Sky Survey, we've been able to watch this process happen over the past 10 or 12 years. We've seen a quasar turn into a normal galaxy as the supply of gas near the supermassive black hole in its center dwindled and got eaten up or ejected, and then it comes out being a normal galaxy.
Isn't that cool that some things in astronomy actually happen in real time? Everything isn't an astronomical timescale. Some things actually, if you watch enough stuff, you find interesting things that happen pretty quickly.
Well, I remember there was a gas blob, or maybe a star, that was moving towards the supermassive black hole at the center of the Milky Way, and astronomers were watching to see if it would blast out the gamma radiation, and it would happen. Even fairly small amounts going into that black hole can be detected.
Yeah. So maybe I've always used the analogy that astronomy is like taking a snapshot of the universe. Maybe instead of a picture, now we have like an Instagram video of the universe.
But, and when you think about what's going to happen, what Morgan brought up earlier with the Large Synoptic Sky Survey, like we're going to see a lot more of these transient events when the whole sky is being imaged again and again and again. We're going to see these differences, and you're going to, you probably will see, oh, check it out, that supermassive black hole just shut off. Oh, and so did that one over there. And that thing just went off.
with enough data, even 5 sigma events become commonplace.
Yeah. Okay, so let's move on to one final story, and this is sort of a big story that's happened. And Kimberly, I'll let you open up with this one, which is that we've got another harassment scandal in astronomy.
Well, it's not just another; it's 2 more that have broken. Two more that have broken in the past few weeks. Both of which are at different universities by different people. Both occurrences happened over many, many years to many different people. And Morgan has many of the details on that he can share, but one of the big takeaways from this is that it wasn't just one person at one university that one time that we had to deal with it. We are have to, as a community, come to understand that this is a large problem across all of astronomy, and not just in astronomy, but across all physical sciences, technology, all of academia, that sexual harassment and other types of harassment are a problem. So I'm going to let Morgan share the details of these new specific cases, and then we can talk about how we can move forward from this.
Right, so we talked last fall about the first of these major cases to sort of break out into the public eye, and it certainly wasn't the first case to occur, and unfortunately we're finding that it's by no means the last case to have occurred as well. But what these two new cases illustrate are sort of the different tracks that this can take, as well as the different tracks that institutions can take in dealing with them. The more prominent of the two that came out this week was a professor named Tim Slater, who is currently an astronomy education researcher at the University of Wyoming. But before being at Wyoming, he spent time at the University of Arizona, in which he engaged in a pattern of physical and verbal sexual abuse to people, both students and employees, under his authority. And after a complaint was filed against him, the university investigated and determined that these complaints had merit, and what they did was shuttle him into sexual harassment training. And after he completed this sexual harassment training, they returned him to the workforce, where he continued to work for 4 more years at the University of Arizona. And that was Arizona more or less following the procedures as stated in the Title IX of the United States Education Act. But what happened next was that Slater left Arizona to move to Wyoming. And Wyoming heard some rumors that Professor Slater had been engaged in inappropriate behavior with students at his previous appointment. But the University of Arizona was unable, under federal law, to share the results of their investigation with the University of Wyoming. And thus, Professor Slater took his appointment, a very prestigious appointment at the University of Wyoming, basically starting with a clean slate. Wyoming had no evidence that that Slater had undertaken any of these actions, and therefore was unable to take any action themselves. The second case was one that happened much more recently, and this was with a professor named Christian Ott at California Institute of Technology, and he's a very prominent researcher in gravitational waves. And he was suspended this week by Caltech for what they referred to as a pattern of gender-based discrimination. And they didn't provide any information or even his name, but media investigations revealed that it was a man named Professor Christian Ott. And Ott, along with Slater, were actually engaged in the same kind of work. Professor Ott had a grant from Professor Slater's research institution to undertake astronomy education. And I think for me this is probably the most troubling aspect of these new allegations, because astronomy educators are the people that we're entrusting with the responsibility of teaching us how to teach and how to excite and how to care for the next generation of astronomers and the next generation of scientists. And to find that instances of sexual harassment and sexual abuse are rampant even within the astronomy education community, while necessarily not surprising, is extremely disheartening for what it says about the future of our field.
Right, and so going forward, there are a few positive things that came out along with these cases. The fact that we are talking about them on the national scale, on the international scale, the fact that we are now talking about this still and bringing these names into light and keeping the conversation going, that is an incredibly positive move forward for the astronomy community, and hopefully spurring other academic communities as well to start these conversations within themselves. Another incredibly positive thing that has happened is that the issue of sexual harassment in academia has made it to the floor of the U.S. Congress with Representative Jackie Speier, who is from California, who is introducing legislation into the U.S. House of Representatives to combat this, the inability for universities that are hiring these harassers to obtain the information contained within Title IX investigations. Now, this was the issue with Professor Slater transferring from the University of Arizona to the University of Wyoming was that the University of Wyoming received no information about his previous indiscretions at the University of Arizona because of how the Title IX system is set up. With the new legislation that is going to the U.S. Congress, Title IX investigations must be shared with new potential employers so that people who transgress and harassers cannot just move to a new university with a completely clean slate and continue their pattern of harassment. So that is another incredibly positive thing that has come out and is bringing a real spotlight into this issue on a national scale. On top of that, there are a number of things that individuals and individual universities can do to continue to combat this type of harassment and other types of harassment. It was very troubling to me to discover that many universities do not require any sort of sexual harassment training for their new employees or staff members or faculty. There is no mandatory sexual harassment or management training in place in many universities. If your university or institution is one such place that does not have sexual harassment training as mandatory for new staff members, please speak up about it. We cannot let this continue to happen. We can't let people skate by on not understanding how appropriate workplace interactions really should be.
And this doesn't have to be just if you're in an academic university. If you're also at your place of work, or even places where you volunteer or interact with a lot of people. All of these sorts of places need to have policies and guidelines for what constitutes appropriate and inappropriate behavior. And without those policies, it's very difficult, sometimes impossible, for these sorts of abusers to be removed from their environments.
Exactly.
Yeah, I had a sort of very frank and interesting conversation with Pamela Gay, my co-host with Astronomy Cast, yesterday. That was our whole topic on Astronomy Cast. Episode 399 was about sort of what it's like to be a woman in science, but also sort of, and she gave a lot of suggestions on both what women who are potentially facing certain levels of discrimination and harassment, and then what we as male allies to the women who are maybe going through this what actions we can take, and then also what recommendations that the schools and sort of the institutions can take to try and really minimize the amount that this happens, because it's it needs to be worked at from all these levels all at the same time, and hopefully we can move back to this for people just doing science as opposed to being jerks.
Yeah, and one more thing that needs to be said is that we're talking about sexual harassment because women are perhaps the largest group of people to experience harassment in the workplace, but they're by no means the only group. People are abused and harassed in universities every day, not just for their gender, but for their sexual orientation, for their race, for their disability, for their religious affiliation. And the sorts of actions that we take to try to protect people from sexual harassment also need to be taken to protect people from any sort of abuse like this, because it's all damaging, and in fact the smaller of a group that you belong to, the more difficult it is for you to have action taken on your behalf, and ultimately the more destructive that abuse will be to yourself as a person, as well as for your future career. And so we need to make sure that we're not focusing too sharply just on one vector of harassment or abuse when there's a whole spectrum, unfortunately, of people who are having to face this sort of behavior.
100% yes.
Yeah. So I look forward to this to being the last time we ever have to talk about this. Because
I look forward to that too, but I don't have my fingers crossed.
No, we've already had to talk about it so many times this year, and we will continue to talk about it so that everybody understands that it just won't be tolerated, and that there's no, it's just not going to be able to continue in these institutions. Okay, well, why don't we wrap things up? So, thank you, Kimberly, for joining us this week. Where can people find out more?
Oh, well, thanks for having me again, Fraser, as always. It's a pleasure. If you want to find out more or contact me about anything, you can look at my Twitter handle at AstroKimCartier, and you can find out more about my work as well as my various blog posts about sexual harassment in astronomy on my website, kimberlycartier.org.
Fantastic. Morgan, where do we find out more?
Well, I've made it my 2016 New Year's resolution to be more active on Twitter, so I recommend you follow me there at Morgan Renberg. Otherwise, you can check out some of my latest work over at morganrenberg.com.
Dr. Paul Sutter, where do we find out more?
Yeah, you can find me on Twitter and Facebook. My name is Paul Matt Sutter. The Matt is important, otherwise you get somebody else who's not me. They might be more interesting than me, I don't know, but it's not me. You can also see all my work at pmsutter.com. I also do another podcast that is not in competition with any of Fraser's fine podcasts. They go together, like puzzle pieces. And mine is called Ask a Spaceman. You can find out more info at askaspaceman.com. You can also help support that podcast by contributing to me on Patreon, patreon.com/pmsutter. And you should give me money because paying your rent is overrated.
Yeah, absolutely. So let me just reiterate here. Go to Paul's Ask a Spaceman podcast. Go to his Patreon campaign. Contribute on an ongoing basis to his campaign to make sure that he gets to make more of these shows and feels a horrible, wrenching guilt whenever he doesn't.
That's
right.
This
is the way I feel. So I think we need to spread the love around. All right. And so, Steve, once again, thank you so much for joining us this week, and thanks for sticking around to answer some of the bonus questions here on the Weekly Space Hangout. We really appreciate being able to get this direct line to NASA and the Kepler team. So thank you so much for joining us.
You're quite welcome. Anytime. It was fabulous. Thanks a lot.
And so I just want to do a big thank you as well, of course, to all of the viewers and to the Weekly Space Hangout crew. This is, of course, really the producers of the show. They choose our guests. They were working so they can tell us the stories they want us to talk about. We're really moving. We really couldn't do this without this amazing community and the work that goes on behind the scenes. So if you want to find out more, just do a search for WSH Crew. Google will take you there, both to the community. Now they have a website. They've got a Twitter feed. It's really sort of becoming a life of its own, which I couldn't be happier. So thanks again to all of their support. And so if you're a big fan of the show, get involved in the community as well. You'll find a lot of like-minded individuals. So once again, Fraser Cain, publisher of Universe Today. If you haven't already, make sure you subscribe to this channel so you get more notifications when we do more of these shows. And if not, we will see you all next week.